Hi folks, welcome back to Physics with Captain Rod. I'm making this video here to provide an example about kinematic motion for rotational problems. This is going to be number 38 here in your OER physics text here. So it says during a 6-second time interval, so I already know that delta t here in this example is 6 seconds. A flywheel with a constant angular acceleration turns through 500 radians. So what that tells me here is that we have a change in theta equal to 500 rads. And it ends up with an angular velocity of 100 radian per second. It's important to realize that's the final velocity in this problem. Whoops, and that's an angular velocity, not a translational velocity. So I'll put omega final 100 radian per second, 100 rads per second. Okay, so then it asks various questions like what is the initial angular velocity and what is the angular acceleration of the flywheel? So if you think back to like chapter 2, early in the course when we were describing motion, we typically did so by drawing and then using velocity graphs. Rotational kinematics is no different. I'm going to start with a graph. And this graph is going to be angular velocity against time, and this will be in radian per second. So, a lot of problems maybe start from rest. This one doesn't. There's nothing in here that leads me to believe it starts from rest. In fact, even question A, what is the angular velocity at the beginning of the 6 seconds, implies there is an initial velocity here. So I'm going to go ahead and assume it starts up here somewhere at some value that we do not know. We end up at 100 radian per second, and it says the angular acceleration is constant, which means that we're going to have some sort of linear graph here. So I'm going to go ahead and assume a linear function out to some point t. Now in this problem, that t is 6 seconds. We do know our final angular velocity here is 100 rad per second. And remember, these graphs have two important properties that we use, slope and area. I'll go ahead and look at the slope. So the angular acceleration is given by the slope because that's what that thing is. The angular acceleration is the rate that your angular velocity changes. So that's the slope of this graph. And using this point and this point, it's pretty easy to write an equation out for the slope. That's going to be 100 rad per second minus the omega initial over t minus 0, or I'll just put 6 seconds. So here's an equation here that would tell us, or I should say there's an equation that comes from the slope of this line, the slope being the angular acceleration. But it's got two unknowns. I don't know the alpha, I don't know the initial angular velocity, which is perfectly fine. We'll go ahead now and look at the second important property of these graphs. This area right here is going to give us the change in theta. If you're having trouble remembering what the area is going to give you, just look at the units. If you take radian per second times seconds, you get radians. That's a change in theta. So our change in theta, 500 rads, is going to equal this area here. And I'm going to go ahead and use my standard method for calculating the area of a trapezoid. That's going to equal this distance plus this distance divided by 2 times this distance. So that's going to be omega initial plus 100 rad per second over 2 times the width of 6 seconds. And you'll notice when we look at this, this has only one unknown. So I think what I'll do here, I'm going to go ahead and just pause this video, grab a calculator, and calculate that unknown initial velocity. So I don't lengthen the video out. Bear with me. All right, I'm back. That didn't take long. So I got an initial velocity of approximately 67 rads per second by solving this equation here. All right. Next step here is now we can go ahead and calculate our angular acceleration. That's now a known value. So we're going to have 100 rad per second minus 67 rad per second over 6 seconds. And it shouldn't take me long to do this. I got about 5.5 radian per second, or 5.5 radian per second squared. So I think that example is all done. Some important points I would like to make about this problem. Notice that the methodology is very similar to how we attack everything in the first part of this course. Where in the first part of the course, we would draw velocity graphs and then use concepts of slope and area to relate the graphs to acceleration and displacements. Same thing here. It's just that this is now an angular velocity graph in radian per second against time. And then slope gives the angular acceleration. That'll typically allow me to write an equation. And then this bound area here gives the change in theta, allowing me to write another equation for this problem. So hope that this example helps. Have a great day.